So the weather is nice today. How about we take a walk into the woods? So if you go to the woods, you can spot different things like wildlife, animals, or kinds of animals. But if you look like very closely and carefully, you might spot something different. A functor for those who recognize that. My name is Michał Pawlik. I work for SiriusXM. I'm a software engineer. I blog about Scala. I occasionally do some OSS work, but that's it about me. So the trees. Let's have everyone on the same page. Everyone on the venue has saw a tree, right? So we can agree that this is how a tree looks like. Hands up. Okay, not everyone agrees. That's what I expected, because this is how a tree looks like. And even better, this is how a tree looks like, okay? So those of you who had like computer science classes or were just geeky enough to read about it, tree in a computer science is something that is represented by a root, and then it can have like leaves or further branches, right, to model stuff. And if we were to model a tree in Scala, where basically we would have something like an enum. We have saw them already today. So this is an enum. Tree is either a branch, so have a value and further kind of branches, or a leaf, so a final value, no going further down. So how's that useful? Have you been to like Daniel's talk yesterday or a few talks today? You saw ASTs, right? By this time, I expect every one of you knows what AST is. I'm not going to explain that. But there are other like applications. In databases, you have like indexes with B trees. But I think the most obvious example is file system, right? You all have computers. You have like the root of your file systems. Then directory is a branch, and file is a leaf in our tree. And this is how it roughly could look like for like your project, for example. And that looks quite nice. How about we try to implement drawing something like that in Scala? So this idea for this talk comes from SiriusXM where I work. We needed to like visualize something about like the test execution. So this is like a real-world example of how we went through the entire process. So the goal for today's talk will not be about like doing the test execution, but we will draw something like this. So we want to show the details about the meetup. I come from Wrocław, so we'll be visualizing visualizing the meetup editions and talks and the speakers in the console, because why not? So let's have a look at the plan. This is how we're going to do it. We will start very simple. We will be drawing like a simple, not nested structure. So we'll probably just start with like a directory with some leaves, right? Then we're going to try to nest it, see how it goes, then model the meetup details, and finally draw the picture that you saw in the beginning. So how do we start? Probably something very simple, like the renderer function will be something that takes the tree and builds a string. We're not doing side effects here. You can print it on your own. The library does one thing, takes a tree, produces a string. Simple as that, right? OK, baby steps. Let's start with something. This is the directory structure that we're going to start with. So we are working with strings first. We will take care of the modeling later. This is what we want to draw. And as the good developers that we are, let's start with writing a test. So our test would look something like this. We will have a tree. You can see that there is a branch, then which is the root, and then a list of leaves that represent the final or the first level thingies. So if you look very carefully, you will notice something probably not usual. There is assert inline snapshot. I'm not going into like the details of snapshot testing, but if you think about how we are going to test like it further, it happens that the only way you could do it is just by testing the string equality, right? And like it's obvious, but imagine that at some point you want to display emojis or like different kind of character. And how do you test? How do you adopt all the tests? Well, basically you just go to each of them and I don't know, you do a regex or whatever, replace it. So there is a library that we have created doing this. You can like scan the QR code. There is a link. I'm not going into the details, but we like really wanted to make the documentation like self-explanatory. Remember about the like red monk kind of thingy for the Scala popularity, so you know the starts count. Yeah, if you didn't manage to take the picture, just reach me out afterwards. Let's get into the implementation. So the very simple implementation, there is like only way we can start, right? The tree that we start with, it is an enum, right? So it's either a leaf or a branch. And we need to decompose that and decide what we do about the details. So if it's a leaf, it's that simple. We just draw some sort of a character and then the value, right? And then the branch is not much different. We just take the value for rendering this branch and then the further things deep. Let's run the test. And because we are using snapshot forest, we will get the nice diff of what is matching or what not. So this is the outcome. As you can see, the last value doesn't really work properly because we should have this L shape and we have this T shape. So let's look into it and try to fix it. So about the missing L shape. We probably, in our code, you probably noticed that we never track if we're on the last element or the first element, nothing like that. So we could try to fix it by just taking the initial part of the branches, mark it as non-last, and take the last element and mark it as last, and then decide about the character. It's very a naive way of doing that, but if we have a look at our test and execute it, it works. So we have finished the first of the few goals that we had. Now, about nesting, right? Let's have another test. The test will look something like this. So we extend our tree. I will have my own home directory added. So we need to adjust the test. The test data looks something like this. So we will have the tree extended, running the test just to see that it is not working, because obviously we never explored the nesting level. Yeah, and let's think about our strategy. Can it even work in this current approach? So what we are doing here is depth-first search. Does it ring a bell? Yeah, half a room maybe? Cool. So depth-first search is the way that we explore the tree in this recursive approach. So whenever we find a branch, what we do is we take the leaves and start running the function further down. So if we have a root, then the root has a bunch of branches. We run it against the first of the branches, then the first of its branches, first of its branches, then as long as we hit the leaf. Then going up and this way. So is this strategy good enough anyway? Let's try to find out by going step by step. So on the left-hand side, you see the representation of the tree that we wanted to draw. And on the right-hand side, you see our expected result. So let's go step by step. First, we try to draw the bin. That's fine. We have this T shape. Let's move on. We have visited the leaf. Now let's navigate to another one. Boot, that's OK. Home works fine. And then we want to go one level deeper, right? And there is this unanswered question, how do I decide what are the proper characters for this one? Because if there is anything further in the tree, then I will need to have a straight line and then something more. But if there is no last node, then I guess this is an L and this is an empty line. Okay? So apparently, we have some limitations of this depth-first search algorithm. And probably if you ask an AI to implement something like that, this is where you're gonna end up with your implementation. And this is one of the reasons why we even started implementing that ourselves, because some of the open source implementations had their limitations. So how do we go about that? Where there is a depth-first search is not the only way of exploring the tree. There is breadth-first search. Does it ring a bell? Okay, I guess to the same people. Okay. You know something about trees, right? Okay. So as you see on the animation on the right-hand side, it goes through the width, right, rather than through to the height of the image. So what it does, it actually uses a mutable queue. So when it finds a tree, it will put all of the known branches onto the queue, but will go through the queue, not through the leaves starting. I don't know if it makes sense, but maybe it will help us to have a look at some code. So if we are to implement breadth-first search, just something that will collect all of the elements in the right order, we would start with a queue. And this is a mutable data structure, and we need something for the result. So we will go with the list buffer. First thing we do is enqueue the root, because we have like nothing else to do. And then we go, as long as the queue is not empty, we want to go over all of the elements. And going deeper, well, if the queue is not empty, what can we do? We'll take the first element of the queue, just a print to have something for the debug, and then a pattern match, because we still have a tree. We need to like decompose it, right? So what do? If we are working with the branch, then obviously take all of its like children, put it on the queue. Otherwise, just append it to the result. Simple as that, okay? Cool. So looking back at the tree that we are working with, what do we expect? We would expect that we first go through all of the like level 0 elements, and then at last go to this my home directory, right? Because it's like deeper. And this is actually what happens when we try to run this algorithm. So you will notice like there is a bunch of stuff on the queue, but the important part is that we went to the inner directory like at the last point. So far, so good. But how does it help us, right? Like we know 2 ways of crawling a tree, but we're not monkeys here, we're programmers. So we can actually leverage this algorithm to like create this additional source of information about the tree. So we could label the directories, but essentially the tree nodes with some like node positioning, so alignment. Naming thing is hard, but yeah, this one is definitely the first of its parent. Then those in the middle are in the middle of its parent. This is the last one of its parent. Now the inner directory is in the middle of its grandparent or ancestor, and then it's the last within its own tree. Okay, this information will help us then draw the right character. So let's model this position or alignment on the tree. Enum sounds like a good idea for starters, and then create this labeling algorithm. So the labeling algorithm will create something like a list or a mapping from the A, which is the value, to the alignments, list of alignments, because we have like a variable amount of nesting level. The algorithm looks very similar to what we saw already, the difference being the type. So we enqueue not the tree itself, but the tree and the previous alignments, and then the output is also different because we output the alignments. Cool. Now, going along, Again, it's very similar to what you saw. The difference being the result is not the value itself, but we attach positions. So you will realize that when you have a branch, we will have a look at the sub-branches. We'll label the head element with first, then the middle with middle, and the last element with last. Just create a list out of it, put it on the queue, and once we visit the tree, just put it to the results. That's it. So going back to like the source of truth that we wanted to create, this is how it looked like visually, and this is the test that we could write for the labeling algorithm that we wrote. So essentially what we wanted, right? The list, it doesn't have any like alignments, then the inner ones just have like first, middle, last, and the inner one has middle, last, so it works as expected. So far so good, the test runs. And I guess we're ready to finally draw like any tree. So first we're gonna run the BFS to get the labeling, then we're gonna run the depth first search to actually do some drawing. How does the final result look like? Very simple. First, the first algorithm, creating the mapping, you will realize that I used to map, because we like produced lists of A to something, we just turned that to map, and then we render this recursive. It is pretty straightforward. So the algorithm that we started, the huge pattern matching, we just extract the mapping for current node. We render a prefix based on the alignments that we know, and once we hit the leaf, we just draw the prefix and the value. Now, how does the alignment rendering look? Very simple. It's just a few rules that if this is the first element or the middle element, but just up to your liking. You can draw the trees in various ways, but yeah, just a pattern match. Nothing sophisticated. Now, one last thing that we need to do is to model the data and draw the meetup info, right? So if you've been to meetup.com, then you probably recognize this kind of like information about the meetups. If you haven't, then you have something to catch up with, because there are plenty of great Scala meetups, and you should look up one in your like area and join to meet the great people. But going back to Scala code, here is how we could like very simply model the events, talks, and speakers. So each event has like the edition, maybe a date. Then there is one or many talks and one or more speakers per talk, right? Also, I have already like added the serialization here so that we can like visualize each of those entities. But there is one problem. We have implemented a tree of string, right? So we know how to print a tree that is constructed of strings, but we don't know how to render a tree of event or a talk or a speaker or a string or like anything, right? Right or not? Are you still with me? Cool. Do you know what time is it? It's not time for lunch yet, but it's soon. This is the time for the F word. And the F word is the functor. So yeah, we're going to the part of the world that some people might consider like maybe more difficult, but why do we need functor for? Well, provided that we can turn event or a talk or a speaker to a string, functor is just something that will turn our tree of that thingy into a tree of string. So essentially the tool that we need for the job, right? Now, functor could be encoded like that. Noel told us about encoding and how it should be like hidden away from us. So we are now the library authors. We take like the responsibility of hiding that. So this is how we essentially like implement functor for this kind of structure. Again, the only thing that we understand how to do on a tree is to pattern match. So let's do this. If we are working with the leaf, if we have a function from like event, speaker, whatever, to string, we just apply the function, right? This is the only like obvious thing that we can do. And if we are working with a branch, well, it's very similar. The value is getting just converted, and then if there is a list of further nodes, this goes recursively. That's it. No magic. Actually, there's like no other valid implementation for that if you follow the types. Cool. So provided that we write this function from event, talk, speaker to a string, which is again a pattern match like we're in Scala, then turning this tree of event, speaker to string is that simple. It's just meetup, map, render, meetup, that's it. We have it. Like functor just solved our problem. And in our test, we could have like a huge data. This probably should be like fetched from the web or something. We could finally use our tree and the tree rendering method to draw this beautiful graph of meetups. And yeah, I guess there are plenty of takeaways that we could have. I didn't want to like have a huge list. There's one. The thing is, Scala is not about FP versus OOP or versus imperative. It's both. Scala is FP and OOP whenever you need it. Yesterday, Martin spoke a lot about convenience, and you saw that we could combine both techniques to our benefit whenever it made sense. For the depth-first search, we did follow the functional kind of paradigm to do the recursive function without mutability and all of that. But for the BFS, it made a lot of sense to just use a queue and use it, hide it from the user so that they don't like hurt themselves. If we needed a functor, then we implemented one, but the user only sees like a map function and that's it. It's not complex to them. They're kind of familiar with that from lists and other collections. So choose the right tools for solving the problem. It's not about like, being in one group or the other. It's not about fighting. It's about using all the functionalities that language provides you this. And I guess, yeah, it would be nice to finish earlier to have more time for the lunch. So that's it from me. Thank you so much for your attention.